Hello everyone. In this session we discuss about adversarial search algorithms. In my previous session I told you about what is adversarial search. We use this as it's a specialized search used in game theory and decision making of AI applications. Let us start with the first algorithm, minimax algorithm. So minimax algorithm is a decision making algorithm used in adversarial search for 2-player and 0-sum games. As I told you, adversarial search is basically used in competitive environments where 2 players are involved and they are competing with each other. So when 2 players are involved competing each other, either one of them win and other one will lose. It is known as a 0-sum games, means if one wins means other will automatically lose. In such environments where 2 players and 0-sum games, if you want to model the such problem and search for a solution, min-max algorithm is a popular algorithm in that situation. So here in min-max basically used in these kind of games. If you see, these are tic-tac-toe, connect 4, checkers, go and Othello. These are all 2-player games where a player has to outplay the opponent's strategies. How it works, min-max algorithm? First we build the game tree and we evaluate the terminal nodes. As I told you, terminal leaves contains the final output of the game, whether win, lose or draw. And we choose the moves so that a player wants to maximize his winning chances. Suppose here this is it's a game tree. Here I am using 2 player names, max player and min player. A game, generally a max player starts the game. Anyone, a max maybe it may be a computer program or human, whoever starts the game. Basically they want to win the game. So max always here wants to maximize the winning chances, whereas his opponent wants to minimize the winning chances of his max moves. That means max player always wants to tries to maximize his winning chance, always try to minimize his winning chances, whose max winning chances, and he wants to win. And in leaves we have a outputs of the game. +1 means you win the game, -1 means lose the game, 0 means it's a draw. Now how this min-max works means, let us play tic-tac-toe game. Tic-tac-toe game, I constructed a game tree of this tic-tac-toe, not from initial state, already because it's a, if we draw it as it will become a very big tree. So what I do, I took a partial tree of this tic-tac-toe. So in partial tree means, suppose this is the x means max. So this is max level. Here at this level is min is playing, at this level max is playing. Here these are all leaves, whatever the leaves, this is also leaf, these all leaves, they show the whether win or lose the game. Now after constructing entire game tree, this is a game, see the leaves. +1 means here x is the max measure, x turn. Here x, what is the tic-tac-toe? If you keep these symbols in a kind of sequence either in horizontal, vertical, diagonal, like x, 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 you win the game. So I assign the score +1. If there is nobody wins the game, like opponent is 0 and your max is x, if both of them nobody wins, the situation is a draw, 0 and 0. If x loses the game, like here opponent min win the game, so here I gave -1. What we do here, first after assigning these scores at the leaves, we go slowly. Now here in this child, this is the terminal node. What is the value? Positive. Max takes the what is the maximum value of its child. Suppose min takes the what is the minimum value of its childs. Suppose here it is plus 1. Someone there is another, suppose in assume there is another node with minus 1 also. Now minus 1 and plus 1, these are the values. Its parent is max. So plus 1 will be propagated to max, because here max parent takes the maximum value. Here it has only one child, so 0 is sent to the parent. Here also one child, 0 is sent to the parent. If any child has a maximum, suppose here it is 5, it is 3. Now it is a maximum level. Suppose now it has no child. Suppose there is a 5 and 3. Now 5 will be given to max, because maximum take the maximum value of its child. Now plus is given to this one. Now minus 1 plus 1. Min player takes the minimum value of its child, who is a minus 1 and plus 1. What is the minimum value here? Minus 1 is sent to the min player. Here also min player, what is the minimum value? Minus 1, 0. Minus 1 is the minimum. We send it to its parent, minus 1. And 0 plus 1 minimum 0. And again max takes the maximum value of these children. So there are 3 values, minus 1, 0. Out of these 3, what is the maximum value? 0. 0 is sent to the root node. Now like this we construct the game tree. From the leaves, maximum values are sent to the maximum player, minimum values are sent to the minimum player. So parent who is the, whether it is a maximum or minimum, we calculate. Once game structure is designed, now here max has 3 possibilities. This is the current situation, current state of the game. Already previous states already is there. Now I started at this current state. Now move is X move. X either you can go in as already decision tree is built by the algorithm and already values are assigned. X move, X has the highest value. Now automatically here game will move into this direction. From this direction again now it's a max player will play this move. Now min player goes to, from here he goes to this one. Again max player wants to, here no options. Because here from here this min player knows that if this is the direction he wants to minimize, so he go in this direction. So game will lose, because already this is the state. If this is the state, you already automatically go into the draw situation. Like this a game tree is designed. Max knows the best move to make by looking at the scores given, built from the terminals. Like this algorithm before starting the game itself, from the current state it draws the game tree of entire game tree and assigns the scores at each level, maximum player level, minimum player level. Once scores are assigned, algorithm automatically makes the move. This is a kind of algorithm, we call it as a min-max algorithm. Second algorithm that is used in advanced search is alpha beta pruning algorithm. Alpha beta pruning algorithm, it is just a refinement of our min-max algorithm. Suppose this is the game tree structure built for a game. There are max player, min player. Now game starts at the max player. Generally if I apply only simple min-max algorithm, now 3 and 5, which maximum value 5 is sent to the max player. Three and 5 is sent to the max player. 6 and 9 maximum value 9 is sent to the E. 1 and 2 is sent to the F. Minus 1 to 0 maximum value 0. From 5 and 9 minimum value is sent to the B. 5, 9, 5. 2 0 0. Again here turn is max. Max selects the maximum value 5. So whenever a game started from the max, max always moves in this direction. First, because it is 5, it goes in the 5. Min always try to minimum, it goes into this 5. From here, max tries to go into this one. So he will end up at that state of the game. This is a normal min max algorithm. But this is a simple tree structure. Okay, 3 levels only. We can easily identify, we can easily assign the values. But as the tree size grows, as the game size grows, the levels of this game tree also increases. At that time, unnecessarily exploring the solutions means, suppose some branches may not give any value to the players, means pruning. What we do, we try to minimize the setching paths. So what we do, we cut down the branches that don't give any value to the player. We call it as a pruning. Alpha beta pruning. What alpha beta pruning means? We take two values, either max term, alpha and beta. Alpha is set with minus infinity and beta is set with plus infinity. See, but alpha is modified by max player, beta is modified by min player. So here also initially let us see it as a alpha is equal to minus infinity, beta is equal to plus infinity, alpha equal to minus infinity, beta equal to plus infinity. Now when we start the game, A either goes in a left B direction or A goes in a C right direction. Suppose assume that A starts with the B. So A comes to the B. Again from B, either I go to the D or E. So let us assume I also come to the D. Now D, next one is 3, 5. 3, 5. So here I calculate one, make alpha equal to maximum of minus infinity 3. 3 is sent to its parent 3. So maximum of minus infinity is 3 is 3. Now here alpha will become 3. Now I check one condition. If beta, here at the leaf level I take the 3. Now 3 is sent to the max player. Max is alpha. Now I calculate alpha equal to maximum of minus infinity to 3. Now alpha is 3. So maximum 3 is the maximum. Now I have updated alpha with 3. Now I check the condition. If beta is less than or equal to alpha is false, then explore next child. If beta less than or equal to alpha true, prune or cut down right child. Means once it is true, you don't need to check for 5. Suppose 3 is now alpha equal to 3, here beta equal to plus infinity. So beta is less than or equal to alpha, it will become false. So when it is false, again I go for exploring 5. Now again 5 is sent to the, now I calculate maximum of, earlier it is 3, now it is 5. What is the maximum of alpha? Now alpha is set with 5. Now 5 is propagated to its parent beta. Now here value, here it is 5. Now beta is a minimizer, calculates the function beta equal to minimum of plus infinity to 5. Here beta is 5. That means here this is a guarantee that at this level, if you whatever explore, minimum guaranteed value is 5 for minimum. That means his estimation value is, at this my estimation is 5. So less than estimation means I don't need to go in this direction. Minimum 5 he expects in this, in his child. Now again is this 5 is here is sent, here already alpha equal to 5. Now left whether you go for exploring E or not, we search. alpha equal to 5, then here already beta equal to 5. Recently I calculated 5. Now I send it 6. Now at max level I calculate alpha equal to maximum of 5 comma 6. So alpha equal to 6. So again I check the condition, is beta is less than or equal to alpha. Here beta is 5. Recently I updated beta value. 5 is less than or equal to alpha, true. So true means I prune, I cut down, no need to again explore this 9. So like this. Now anyway alpha is updated with 6 and there is no need to propagate, it already beta is 5. Now beta is sent to its one 5 A. Now A is 5, A is expecting 5. So again at A calculated maximum of 5, alpha equal to 5. Again at this level beta equal to 5, alpha equal to 5. We check right side of the C, we apply the same process. At one point we can prove the G also. Like this alpha beta approach prunes the game tree and it tries to cut down the maximum possible setching process to reach the goal state. Like this we apply. Thank you.